Welcome to the video lecture EE-371 Electromagnetic Field Theory. In last lecture we have obtained the capacitance in between conducting boundaries having different structures. The structures were in rectangular form, cylindrical form and spherical forms. In those structure we had applied the electrostatic field theory and the boundary condition, and finally we had defined the capacitance between different structures conducting boundaries. In this lecture you will learn the graphical method, which is an approximate method, and this method is also known as curvilinear square wave method. This is an approximate method which you can apply even to determine the nonlinear behavior which is produced at the edges corner of a conducting plates. You will also learn that how to use Poisson's and Laplace's equations to determine the capacitance in between two conducting boundaries. This is Dr. Husnul. So before going into detailed discussion, let us first solve the drill problem which we have left in last lecture. This is drill problem 6.3 on page 154. In this problem we have asked to find the capacitance per unit length between cylinder and a conducting sheet, and the maximum surface charge density on the cylinder. We have given a conducting cylinder of radius 1 centimeter and at a potential of 20 volt, which is parallel to the conducting plate, which is at zero potential. The plane is 5 centimeter distant from the cylinder axis. Look at the figure. So the cylinder is represented by a circle of radius b. In meter, the value of the radius of this cylinder is 0.01 meter, and potential on this cylindrical surface is 20 volt. The conducting sheet is located at x equal to 0, having 0 potential. The distance between the cylindrical axis and the conducting plane is 0.05 meter. The relative permittivity of dielectric material in which the cylinder and the conducting sheets are embedded is equal to 4.5. So in last lecture we have obtained this value. For the case when B is much smaller than H, then we can use this formula. So the capacitance per unit length is equal to 2 pi epsilon naught epsilon r divided by ln 2h divided by b. So plug in the values of epsilon naught epsilon r, h and b, and after the numerical manipulation we obtained the capacitance per unit length, which is equal to 108.84 picofarad per meter. Our result is very close to the answer given in the book. In order to determine the maximum surface charge density, so remember that the surface charge density is maximum in between the conducting sheet and the cylinder, but it has minimum value in the absence of the conducting sheet on the conducting cylinder. For example, on the right side of the cylinder, above and below the cylindrical shape, the surface charge density would be minimum. In order to obtain the maximum surface charge density, we are going to use the foregoing relation which we have obtained in last lecture. So first we need the magnitude of D field. This D field is the electric flux density between two conducting cylinders. So taking the magnitude of this field, and as I told you that the maximum value exists at the left side of the conducting cylinder, because the face of this on this side, the face of the cylinder on this side is directed to, is in parallel to the conducting sheet. So that's why the surface charge density at this location is maximum. This location is denoted by H minus B, which is equal to 0.05 minus 0.01, or it is equal to 0.04 meter, and y in this case equal to 0. So plug in these values, replace x by h minus b and y equal to 0 in this relation, and some mathematical manipulation, we obtained this formula, that is the maximum surface charge density is equal to minus rho L divided by 2 pi into 1 upon h minus b plus a, plus 1 upon h minus b minus a. In this relation, we need the value of a and the value of rho L divided by 2 pi, which we can obtain using the value of h and b given in the problem. So A, which represent the position location of the line charge, is equal to square root h square minus b square, so which result in 0.049 meter. The square root k1 is equal to h plus square root h square minus b square divided by b. Plug in the values of h and b, which result in 9.9 value. The square root k1 is dimensionless quantity. Now we have obtained this relation in last lecture. Using this relation, we can easily define the value of rho L over 2 pi, which is equal to 3.48 into 10 power minus 10 coulomb per meter. Using the value of rho L divided by 2 pi, the value of h, b and a in this relation, finally we calculate the maximum surface charge density at x equal to h minus b location, which is 34.71 nanocoulomb per square meter. But this result is not perfectly matched with the result given in the book. I think there is some error, or the answer given in the book is wrong. Now let us discuss the curvilinear square map method. This is an approximate method. This is also known as graphical map method to estimate the capacitance between two conducting boundaries. This is also known as that how to use field sketches to estimate capacitance in two-dimensional problem, two-dimensional boundaries. Uh, by two-dimensional boundaries, we means that there is no variation in normal direction to that structure. Before going into detailed discussion, let us highlight some concepts which we have discussed in last lectures. As you know that the conducting sheet behave like equipotential surface, so the D and E field are always in normal directed in normal direction. Um, Now let us consider a single charge. So whenever we want to determine the E field or D field due to a single charge, so by virtue of Gauss's law, we enclose that charge into a hypothetical surface, closed surface. That closed surface is known as Gaussian surface, but that closed surface also behaves as a equipotential surface. So the charge enclose you can enclose the charge in different Gaussian surfaces which represent equipotential surface. That is, a single charge may be enclosed in a spherical Gaussian surface, so that's spherical Gaussian surface represent equipotential surface. For example, in this case, we draw two equipotential surfaces around the point charge. Similarly, for example, we have a line charge, then line charge produce equipotential surfaces in the form of cylinder. Now let us come to the detailed discussion of what is curvilinear square map method, or what is the graphical method. So let us consider two conducting boundaries which are denoted by red curve, that is on the left and right side. The left conducting boundary is connected with high potential, and the right conducting boundary is connected with zero potential. The depth of these conducting boundaries are 1 meter into the screen or paper. So as we know that the electric lines of forces are streamlines originated from high equipotential surface and terminated on low equipotential surface. So the green line which start from A and terminate on A prime represent a streamline. Similarly, when another line start from B position on left conducting boundary and terminate on the B prime position on the right conducting boundary. So the two streamlines combined together, these two streamlines produce flux tubes. We call it flux tubes. The length of the length in between A and B is denoted by delta LT, where T represent tangential length along the boundary, and the depth of the conducting boundary is 1 meter into the screen. So in this flux tubes, the fluxes which are originated at the average of this surface are flux terminate on A prime B prime plane. So that means the fluxes are confined in between this flux tube. Now this is known as flux tube. Along the boundary, we have flux tube which start from high equipotential conducting boundaries and terminate on the low equipotential conducting boundary. Now we can also divide the space in between two conducting boundary into a large number of equipotential surfaces. The equipotential surfaces in between the two conducting boundaries are represented by green lines having constant potential difference, that is delta V, del V. Del V is constant potential difference in between any two equipotential surfaces. So the combination of the combination of flux tube and equipotential surface define curvilinear squares in between the conducting boundaries. This method is known as curvilinear square map method. That is how to divide the space in between conductors into curvilinear squares, as the boundaries are not perfectly planars. So that's why the squares are not exactly similar to the square in case of planar conducting boundaries. So that is why we call it curvilinear squares. Curve. The green line represent flux tubes, and you can count these flux tubes along the boundaries, and the cells, the squares in between the conducting boundary represent um, the cells in between any two equipotential surfaces. So the cells are directed, cells are drawn in between the two conducting boundaries. So they are in the sides of this one of the square curvilinear square along the boundary is denoted by delta LT. But remember that the depth of this conducting boundary into the paper is 1 meter, and in normal direction the side of the single square is denoted by delta Ln. This is in normal direction, so that's why we denoted this by delta L sub n. The potential difference between two equipotential surfaces is delta denoted by delta V. So combine the combined graph of flux tubes and the equipotential surface produce curvilinear squares in between the conducting boundaries. So that is why this is known as a curvilinear square map method, or the field sketches in between the conducting boundaries. Now, for example, a delta psi flux originated from a left conducting boundary, so that much flux terminate on the uh, in the same flux tube, that much flux terminate on the left conducting boundary in the same flux tube. Similarly, for example, if I consider this one, so in this case again delta psi flux originated from left side and terminate on the right side. Similarly, in this case, in this case, and in this case, in all flux tubes, the fluxes are directed from left side to right side, and the um, equipotential surfaces produce the curvilinear squares. So let us develop the mathematical formulas. That is D in this case is equal to delta psi, where delta psi represent that this much amount of electric flux originated from this face of the flux tube and terminated on this on the same flux tube on the left side. So delta psi divided by delta LT. Delta LT represent the tangential length of the flux tube along the boundary, and the depth of the conducting boundary into the screen is 1 meter. So using this represent what coulomb per square meter, which is the unit of electric flux density. From the electric flux density we can easily obtain the electrostatic field, which is equal to 1 upon epsilon delta psi divided by delta LT. So we denote this by equation number 1. We can also define the electric field in terms of potential. So in between the conducting boundary at any curvilinear square, we can define the electrostatic field, which is given by delta V divided by delta Ln. So this is our equation number 2. Combine equation number 1 with 2, so that result in equation number 3, where we in this method we keep the value of delta LT to delta Ln constant. That is the ratio between the tangential length of the flux tube and the normal length of the flux tube, or the curvilinear square, is usually taken as constant, and usually this ratio is equal to 1. So we obtain these three relations, and we will be using equation number 3 in onward calculations. We can also use equation number 1 and 2 to calculate D field, E field using the curvilinear square map method. How to calculate the capacitance using curvilinear squares in between the conducting boundary. So look at this figure. The red curve represent the conducting boundaries, and we have filled the space between the conducting boundaries into a large number of curvilinear squares. The green line represent the streamline, and when we consider two streamlines, so that represent a flux tube. The blue line represent the equipotential surfaces. So C in this case, as we know that the capacitance is defined as the constant ratio between charge to potential. So in this case, uh, as you know, there are, for example, NQ flux tubes. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the in all these flux tubes, delta psi coulomb flux is originated from a left conducting boundary and terminated on the right conducting boundary. So NQ represent the total number of flux tubes. Delta psi represent the fluxes. This much flux or charge originated originated on left conducting boundary and terminated on right conducting boundary, divided by NV del V, where NV represent the total number of curvilinear square. For example, in between, we actually count the curvilinear squares in between the conducting boundaries. That is, for example, 1, 2, 3, 4, 5, 6, 7. So for in a journal, we represent this by NV times delta V. Delta V represent the constant potential difference between the equipotential surfaces. So using equation number 3, this one, we can replace delta psi divided by delta V by epsilon times delta LT divided by delta Ln, which result in this relation. That is, the capacitance in case of curvilinear square map method is equal to epsilon time NQ divided by NV, where NQ represent the total number of flux tubes. We count the flux tubes along the conducting boundary. A single flux tube consists of two streamlines. Two streamlines combined together produce flux tubes. NV represent the total number of curvilinear squares in between the conducting boundaries. So this, we will be using this relation in onward in order to define the capacitance in between two conducting boundary while using the curvilinear square map method. So let us consider a structure, a coaxial cable or coaxial capacitor such that the inner conductor of this coaxial capacitor is in square form that has high potential. The outer conductor in this case is in cylindrical form, which uh, we have represented by a circle, and this the outer conductor is connected with the zero potential. So we are in position to apply the curvilinear square map method to this structure. That is how to apply the curvilinear square map method in between the inner conductor and outer conductor of this structure to define the capacitance of this coaxial cable, coaxial capacitor. So whenever you want to apply the curvilinear square map method, so first of all you will check the two-dimensional boundary for big symmetrical flux tubes. That is, in how many big symmetrical flux tube we divide the space between the inner conductor and the outer conductor. So we know that the streamlines from the corner of any conducting sheet originated in normal direction and terminated on the outer conductor. So or in first glance, we see that we can divide the space between the inner conductor and the outer conductor into four big symmetrical flux tubes, which we have shown in figure B. That is the streamlines from the corner of the inner conductor originated and terminated on the outer conductor. So we split the space between the inner conductor and outer conductor into four bigger symmetrical flux tubes. One, two, three, four. All the four flux tubes are symmetrical. For example, the image of this flux tube is looking below the inner conductor. Similarly, left and right are symmetrical flux tubes. Now, further, you will check that whether we uh, include more symmetrical flux tubes or not. So, in this case, the answer to this question is yes. We can further divide the space in between the two conducting boundaries into more bigger symmetrical flux tubes. So from the mid of each side of the inner conductor, we can draw a streamline which terminate on the outer conductor conducting boundary. So in that way, we can include more big symmetrical flux tubes. So which we have denoted by or highlighted by green line in figure C. So the total number of big flux tubes becomes 1, 2, 3, 4, 5, 6, 7, 8. So we have actually divided the space in between the two conducting boundaries into 8 big symmetrical flux tubes. Now the rest of the work is easy. Just fill one of the big flux tube into sub-flux tubes and curvilinear squares. Then you can easily define the capacitance of this structure. So let us first draw the equipotential surface in one of the big flux tube, there which in figure D we have shown that by green lines, that is 1, 2, 3, 4, 5. The green line represent the equipotential surfaces in between the conducting boundaries. Now let us draw the electric fluxes. So two electric flux are streamlines combined together. They form the flux. So we in this way we can easily divide the the big symmetrical flux tubes into curvilinear squares. You will have exact result if the number of curvilinear square are large in number. So then you will have a result very close to the result which we obtain using analytical formula. So in this case, along the boundary we measure the total number of flux tubes, and in between the two conducting boundaries we count the total number of squares. So in this case, the NQ value in a single, that is NQ represent the number of flux tubes. So in a single big flux tube, the total number of flux tubes are 1, 2, 3, and 4. And we have 8 flux tubes in between the two conducting boundaries, inner conducting boundary and outer conducting boundary. So in the space between these two conducting boundaries we have total number of flux tubes which are 8. So multiply 8 by 4, so which is equal to 32. And how to count the total number of squares in between the conducting boundary, which we denote by NV. So the total number of curvilinear square in between the two conducting boundaries are 6. That is 1, 2, 3, 4, 5, 6. So now we can use the foregoing formula to determine, to measure the capacitance between the conducting boundary inner of a coaxial cable. The inner conducting boundary is in a square form and the outer conducting boundary is in cylindrical form. So using this relation and plug in the value of NQ, where NQ, this is 4. Remember, 4 times 8. So simplify these numerical values. So finally we come across this result, that is 47.22 picofarad per meter. Using curvilinear square map method, you can also measure the value of electrostatic field. For instance, let us consider this big flux tube, and we want to determine the measure the electrostatic field at any uh, curvilinear square to the right side of the inner conductor. So for example, let us consider two units, curvilinear squares. We want to measure the electrostatic field two curvilinear squares away to the right side of the inner conductor. So you can use this formula for as the potential on the inner conductor is V naught. So the potential on the equipotential very close to the inner conductor would be V naught minus 1, and that the equipotential the potential difference on the next closest equipotential would be V naught minus 2. So and let us consider that the length delta LT divided by delta LN, as I told you, that usually we keep this ratio equal to 1. You can consider any value. So, but usually we keep this value equal to 1. So, let us suppose that the side of the square in normal direction of a single square is 1 meter. So per two squares, delta ln become 2 meter. Uh, so fine, after some mathematical manipulation, we come across this formula, that is E equal to V naught minus 1.5 volt per meter. For instance, the potential on the inner conductor is 16 volt. Then you for 16 volt potential on inner conductor, we obtain the electrostatic field to the right side of the inner conductor in 2 curvilinear square equal to 14.5 volt per meter. So using curvilinear square map method or graphical method, you can easily define the capacitance in between two conducting boundaries, and you can also determine the value of E field, D field. You can also obtain the surface charge density using the curvilinear square map method. Uh, in this method, we actually divide the space between the conducting boundaries into a large number of squares. Then those counting those squares, we can easily obtain the capacitance, electrostatic field and D field.